Here we are, question 6. A simple pendulum of length L consists of a small bob, a metal sphere of mass M hanging by a light thread from a fixed support. And we've got a diagram to show that. Show that when the pendulum is at small angle theta to the vertical, the bob's acceleration in a direction at right angles to the thread is approximately A equals G theta. You may add to the diagram. So if we think about what's going on in this setup, I've got some tension force acting like that. I've got mg acting like vertically downwards. A direction at right angles to the thread. So the tension cannot possibly produce any force at right angles to the thread. The tension has to be along the thread. So what we need to think about then is resolving the weight mg into components that are perpendicular and parallel to the thread. And if we do that, we can see from our diagram that this perpendicular component is equal to mg sine theta. So the diagram labeling, sort of adding that to the diagram is probably enough, but I'm going to write the words anyway. So I'll just, to make it absolutely clear, the component of weight perpendicular to thread, or at right angles to thread, that is equal to mg sine theta. And notice it says this is a small angle in bold. So small angle approximation is that sine theta is approximately, so small angle implies that sine theta is approximately theta when measured in radians. Therefore, our force is given by mg sine theta is approximately equal to mg theta. And then the final step here is to say F equals ma. So therefore, mass times acceleration is approximately mg theta, and I can just cancel those m's to get that a is approximately g theta as required. So small angle approximation and resolving that weight into components perpendicular and parallel to the thread. Part 2, graph of velocity against time is given for a pendulum swinging through small angles. So this small angle business is important. A pendulum swinging through a small angle approximates to simple harmonic motion. And that's what we can see in this graph. This is sinusoidal. Show that the length of the pendulum is approximately 0.5 meters. So from our formula sheet, the time period of a pendulum is given by 2 pi root L over G. So this is just going to be a substitute. We can read the time period directly from our graph here. So where I've marked here, that is one complete cycle from 0 through to 1.4 seconds. So from the graph, t is 1.4 seconds. Always just worth, anytime you read something from a graph, always just worth checking the scale. This scale is in seconds, but frequently graphs are given with the scale that may not be in seconds, maybe in, for example, minutes or some other unit. So it's always worth just double checking. That'd be a very long pendulum, I feel, if this was a scale in minutes, but always worth the check. So now this is just put that into our equation, rearrange and solve. So dividing both sides by 2 pi, squaring. Let's just square everything and multiply by g. And that will give me L. So therefore, let me just grab the calculator here, put everything in. Yep, so 0.488 meters, which is of course approximately 0.5. Worth noting though, when you have this type of question, when you've got a question that says show that, and then something is approximately whatever, do not simply sub your numbers in and then say that's approximately 0.5. Always calculate the exact value, because by doing so you're showing the examiner that you have checked that the expression you have does actually produce something that's approximately 0.5. Whereas if you simply put those numbers in and then say that's approximately 0.5, have you checked that, or are you just assuming that that is the case? So always give that exact value. There is no requirement then to say that that's approximately 0.5. You don't need to say that. That is clear. Okay. The mass of the bob is 0.12 kilograms. Show that the maximum kinetic energy is approximately 2 millijoules. So maximum kinetic energy is going to be when the velocity is a maximum. That's going to be a half Vmax squared. And we've got a graph here of V against time. So we can simply read Vmax off our graph. Again, always be careful with the scale. This is in meters per second. So 0.2 up here. So that looks suspiciously like 0.18. So then it's just a substitute. Again, check the units. These are kilograms, so no problem there. A half times 0.12 times 0.18 squared. And hopefully that, again, to show that something is approximate, but I will give an exact answer. And I've got 0.00194. Which is, and that's in joules, which is 1.94 millijoules. And that's it. I'll leave it like that. That is clearly approximately 2 millijoules. Okay. On the blank grid, sketch a graph of the bob's gravitational potential energy against time. The upper graph is provided for reference. Take GP to be 0 when the bob is at its lowest point. Okay, so have a careful think about this. We have got a pendulum set up. Here is a bob, and it is going to swing through an arc to here, backward and forward. At this point, it's at its lowest, and we're saying GPE is equal to 0. This is also the point where it is fastest, and it could be going in either direction at top speed. And then over here, this is V equals 0, but GPE max. And over here, this is V equals 0, but GPE max. So anytime velocity is 0, the GPE will be a maximum. If we think about the total energy in our system is constant, so I'll just write that over here. E total is a constant, and the kinetic energy is proportional to V squared, and V is given as, if I look in the formula sheet for simple harmonic motion, V is given as minus a omega sine omega t plus epsilon. So therefore the kinetic energy graph will be a sine squared. So if I think about squaring this sine graph, what I get is a sine squared graph oh my goodness, my sine squared isn't great, is it? And if I think of GPE is the total minus that. So I need my GPE, as I kind of noted over here, that when V is 0, GPE is going to be a maximum. So we'll put our maximums every time V is 0, we have a maximum. Every time V is 0. So those are our max points. Every time that every time that V is a maximum value, the GPE is 0. So here, that's our 0 point, here, 0 point, here, a 0 point, and here, a 0 point. So well worth kind of sketching those on before you attempt to draw your curve. There's 3 marks for this, and likely those 3 marks are going to be for having these important times correct, you know, the peaks in the right place, the zeros in the right place, and the correct general shape of the graph, which should be sine squared shape. So a smooth curve. Oh my goodness, my oh yeah, that's quite hard to do on a graphics tablet. I feel like I maybe could do a better job with pen and paper, but you would definitely do this in pencil so that you can kind of rub it out if it all goes horrendously. I would hope that this last bit may be a bit iffy. If I try and rub it out though, I think it'll rub out the whole thing. Oh no, I can do something about that. I can hopefully improve that a little bit. Hang on. To some sort of smooth curve. Oh, it's not better, is it? Anyway, that's the general idea. The important thing to note really is those key points. Just kind of getting your head around the idea that the GP is going to be a maximum when the velocity is 0, and that the GP is going to be 0 when the velocity is a max or a max or min. So yeah, getting those points marked onto the graph kind of gives you an inkling as to the general shape. Calculate centripetal acceleration of the bob at the bottom of its swing. Now this is the centripetal acceleration of the bob. That is, yeah, we've got to be really careful here. This could very quickly become confusing because our bob is, from this diagram that I've got on the right, when the bob is at this point, it has a centripetal acceleration towards here because we can approximate its motion to circular motion. And that centripetal acceleration will be equal to a omega squared r, or v squared over r is probably the more useful version to use. If you use the omega squared r, do not confuse that omega with this omega. They are not the same. This is the angular frequency for the simple harmonic motion, whereas the omega here would be the instantaneous number of radians per second it's passing through in terms of this angle theta changing. So we've got to be really, really careful here that we don't confuse this centripetal acceleration with the acceleration of the bob back towards its equilibrium position. So basically don't confuse this acceleration with this one. They are not the same thing. So for calculating this centripetal acceleration, we'll use v squared over r. It's at the bottom of the swing, so that's when v is a maximum. So we can simply read v off the graph. Again, it was 0.18. And the radius of our motion here is the length of the pendulum, which I have forgotten, 0.488 meters. And we'll chuck that in the calculator. give 0.066 meters per second squared. Yeah, sorry, I just wanted to check that. Yep, that was the right length. Yep, so that's the acceleration. At the bottom of the swing, the tension in the thread is greater than the width of the bob. Explain why this is so. Well, you know, look, this is the second part of this subsection. So, you know, that tells you that your answer here is, you know, following on from the previous thing. So the fact that this has a centripetal acceleration implies that there is a resultant force. So there must be a resultant force. And in this case, that resultant force must be upwards. So that resultant force is equal to, it must be equal to the tension acting upwards minus mg. Therefore, tension must be greater than mg. Because we have to have a non-zero resultant force. Hopefully that makes sense. Yeah. So the fact that our bob has this, you know, the clue was very much given in part one here. The fact that there is this centripetal acceleration means that the forces can't be balanced. If T were equal to mg, those would be balanced forces and there couldn't possibly be a centripetal acceleration. Okay, there's more of this question. Describe briefly how you would investigate forced oscillations using a mass and a spring as the oscillating system. As in the setup shown below, and describe carefully what you would expect to find out about the amplitude of the forced oscillations. This is a 6-mark QER. So bear in mind, QER questions, normally if you have a question that's asking you to explain or describe something, the number of marks relates to the number of points that you need to make. So if you're asked for an explanation and it's a 3-mark question, then you can think about the idea that you need to be making 3 points. The mark scheme is going to recognize 3 points and give you 1 mark for each. When it's a QER, that is no longer the case. So remember that QER questions are marked in bands, and you basically have a top, middle, and bottom band. Top is the 5 to 6 mark band, the middle is the 3 to 4 mark band, and the bottom band is the 1 to 2 mark band. I mean, obviously you can score 0, but those are the 3 bands, top, middle, and bottom. And in general, the physics in your answer gets you into one of these bands, and then whether you are at the top of the band or the bottom of the band depends on the QER aspect. So QER stands for quality of extended response, and what decides whether you are at the top of the band or the bottom of a band is that quality of extended response. So that is things like, is your answer presented logically, in good English, you know, those types of things. Have you used appropriate technical vocabulary and that sort of stuff. So a logical structure to your answer. But overwhelmingly the important thing is that you get yourself into the top band. And that comes from the physics in your answer. So an approach to these questions, read the question carefully, describe briefly how you would investigate these oscillations, and then further we've got and describe what you would expect to find. So the way I would approach this, I've been asked to describe 2 things. So I would have those as headings. If not physical headings in my actual answer, mentally I would be treating this as a kind of 2-part question. First, I want to describe how I'm going to investigate this. and then I'm going to describe what I expect to find. In general, mark schemes for these sorts of questions tend to have a list of points that they call indicative content. So the mark scheme will likely have a list of points about this first section, about the investigation, and it will have a list of points about this second bit. To get into the top band, the mark scheme will most likely say you must have at least, perhaps 4 or 5 of the points for the first section and at least 4 or 5 of the points for the second section. So what we want to do is lay out our answer in a reasonably structured way, possibly with headings, and then try and make as many points as we can about the physics that's relevant to that. So that's the exam technique for the approach to this type of question. Let's have a look then at the actual physics in the question and see if we can get our heads around that. So this is about forced oscillations, and the whole idea with forced oscillations is that we take a simple harmonic oscillator and we make it oscillate at a given frequency. So this question is essentially about resonance. So what we've got here is a signal generator, a vibrating pin, a spring, and a mass. The very brief version of what we're going to want to do here is we're going to want to take some note of where it is when it's in equilibrium. We're going to want to adjust our signal generator so that this pin vibrates at some frequency f. The mass will therefore vibrate as well, and we will make a note of the amplitude of the oscillation. Then we'll change the frequency that the vibrating pin is moving at, and we'll measure the amplitude again, and we'll continue to do that for a large range of different frequencies. What we should find is that at one particular frequency we'll have a very large oscillation, indeed, and at that particular frequency we would expect the frequency of the vibrating pin to match the frequency that this mass oscillates at if it's allowed to oscillate freely. So hopefully that theory sounds familiar. Hopefully that is recognizable as I'm describing resonance. I'm describing the idea that if we force an oscillating system to oscillate at the frequency that it would naturally oscillate at, then we get a very large amplitude. So that's what this question is about, really, and we just have to think about how do we describe that process clearly. What is it we're going to measure? How are we going to measure it? What are we going to vary? How are we going to vary it? And then in the second part, we need to describe what we would expect to find. And what we would expect to find is, as I said, that there would be a very large amplitude oscillation when the frequency roughly matches that natural frequency, and the rest of the time we would expect a much smaller oscillation. So I'm not going to go through because it'll take quite a long time and I've probably talked enough. But what I'll do instead, rather than going through in great detail, I'll just very briefly bullet point the types of things that I would expect. So for the experiment, we might note position of the bottom of mass on the ruler when stationary or when in equilibrium. Then we might turn on our signal generator at a very low frequency. Whoops. And we'll note the maximum displacement of the oscillating mass. i.e. its amplitude. Then we'll change the frequency. Note amplitude again. And we'll repeat that process for a wide range of frequencies. So we might want to mention a couple of other things about our experiment. We might want to add some detail about how we could improve this experiment, make it slightly more accurate. We might want to mention that in between measurements we'll allow the mass to come to rest again before continuing, just to make sure that we're getting a true representation of what the amplitude is. I didn't close that bracket. The second part then is about what we would expect to find out. So the kind of results from our experiment. I would be tempted to plot a suggested graph. So if we were to plot amplitude versus frequency, we would expect something like this. And hopefully this graph looks familiar. Let me redraw those. So amplitude, frequency. We'll have something coming up to a tall spike and then tailing off again. And if I just label this F0, then we'd want to add some words, some description of this, the idea that at low frequency we have arbitrarily small amplitude oscillations. At very high frequency we have essentially zero amplitude oscillations. We have a sharp spike in amplitude near F0, and I'd probably want to mention that F0 should match frequency at which the mass oscillates freely. Something along those lines. So I would add a little bit of detail about describing this, and this effect is called resonance. And that's about it.